especially those, there are some videos for these professors from, I think, University of Washington. They run a YouTube channel where they record their lectures. So they have some very good lectures on principal components analysis I shared. Hopefully you had an opportunity to look at them. Okay, so I'll share my screen in a minute. So I'm using RStudio. At some point I was planning to put this document in an R Markdown file. It's easier to teach when it's in that form. Give me a minute. Hello? Yes. Nico Salam, I'm trying to do this data science class. Yes. Oh, which one now? Okay, the one who came to visit. I think you came with her. Yeah. Okay. Okay, I had to respond to the chair of department. So, but now we can continue. So, can you confirm that my screen is visible?
Yes, Dr. The screen is visible.
Good. So, some of these concepts are already familiar. So that's why I'm thinking just running through the code will still be sufficient for now. So there's this package called the ML bench package. It contains some data that we need. And in particular, there's this PIMA Indian diabetes. We can run it. We can load it now. This PIMA Indian diabetes 2, it comes with this package ML bench. Now we can find out more about the data. So as usual, we can do the question mark, and then we are using this second one. Let's run it and find out more about the data. So this is a description. It's a data frame. We have 768 observations and 9 variables. So the description is here. It's contains a corrected version of the. There's a first version. I don't know much about the first version, but there's this. I think it's University of California or this UCI repository where you can find the data if you wish. So these are the variables. And also there are some links here if you want to go to those links and see them. So these are the variables that are in the file. The first one shows the number of times it's women, this one mostly, so the woman has gotten pregnant. The next one is the plasma glucose concentration, diastolic blood pressure, triceps, skin fold thickness. Some of these are just medical terms. I really don't know what they mean, but at least you can see them. Then this last one is diabetes. It's I think is it 0 or 1 or yes or no in terms of values, but it it tests whether someone has diabetes or not. It is a categorical variable. So it indicates whether someone has diabetes or not. So I think now we have a picture of the data that we're dealing with. So now that the data has been loaded, we can try to visualize the relationships between these two variables, mass and pressure. Maybe we can go back and look. So pressure was the diastolic blood pressure in these units, and mass is just the body mass index. So this is BMI. So mass, this variable mass simply captures, it covers the BMI, which is the weight divided by the square of the height in meters, weight in kgs and square of the height in meters. So we want to compare those two using a scatter plot. I believe you're familiar with this ggplot and so on. Do I need to explain anything? It's important that you speak. Otherwise, I really don't know whether I'm in the right direction.
Yes, okay. For ggplot, we are familiar with.
Okay.
Yeah.
Good. So we're going to do the scatter plot of mass and pressure. That will give us a rough idea of the kind of relation there is between the two variables.
Hi, Mwalimu.
Yes.
Okay. Some of us are struggling with bandwidth. Sorry, can we please turn off the videos? Maybe we are losing you a bit.
Oh. Actually, I intended to put off the video. Now things should be better.
Yes, and I think some people are saying they are in the waiting room to be let in.
Oh, these are the latecomers.
Thanks.
Let's allow them in. So let's make sure everyone. So try to, when you join in, please use your full names. I need to be sure we have the right people in class. Sometimes we can get strangers in class. So try to use your full names when you join class. It also helps me with taking attendance. Okay, so you can see what it looks like now. If you do the scatter plot of pressure by mass, it seems to generally indicate that as the mass goes up, the pressure also goes up. Of course, there is a lot of variation, but in general, the trend seems to indicate that there's a positive correlation between mass and pressure, right? So this means that a line, if you fit a straight line on this, it wouldn't be such a bad idea. You could try and check the model when you fit a straight line on that. So we look at, again, these two, triceps and mass, but this time we color using this indicator for diabetes, whether they have diabetes or not. So we see whether there's any connection between diabetes and this one. So negative is this. Negative means they have no diabetes. Positive means they have diabetes. So a number of the negative ones seem to be where the triceps are smaller, and or rather it was about the skin of the triceps are smaller, and the mass is also lower. So these really high ones, you can see the ones that have extreme mass seem to be more susceptible to diabetes. They are the ones that are positive. Of course, you have some in between. There are some intersection between the two, but when you go to the extremes, they seem to be more prone to getting diabetes because you can't see the negative ones on these extremes. Again, here the relationship seems to be linear. It means as the higher the body mass index, the thicker this tricep skin, if I remember correctly what that variable. But basically, there's a positive correlation between these two variables. And also, if you consider this, if you condition it with this diabetes, you can see it seems to suggest that the higher extreme values seem to suggest that such people will be more susceptible to having diabetes. So again, that's we are not fitting lines yet. We are just exploring the data. So what is next? So I will run this, I think, since you're familiar with the details. I just run it and then we look at the graph. So here we have drawn this graph and annotated it. Again, we have tried to color it using this numerical variable. That is the number of times someone has gotten pregnant. But this one doesn't seem to have any pattern on these variables. But again, to check, one way you normally check if there's positive correlation is you draw the mean of the variable on the x-axis. So this vertical line here is right at the mean of the vertical, or it's right at the mean of this mass. So the mean is around 30 something here. And the mean for triceps is around 25. So if you draw these lines, positive correlation usually requires that the majority of the points are in this quadrant, So that gives a good possibility of strong positive correlation. Again, we're still just exploring the data. We shall deal with the details later. So how you measure this correlation is usually use covariance. And here you compute the covariance for each. Here, the higher the covariance, the stronger the correlation usually. So here we have 24 for the first pair of observations and 46 for the second pair. So they're both positive, but one is a weaker positive correlation than the other. Now, the only problem with covariance is it's sensitive to the magnitudes of the values. So the large values give large values of covariance, so it may not be possible to compare covariances in a meaningful way. To counter that, you can compute the correlation instead. So correlations also indicate the same thing. I think you're familiar with correlations. They are indicators of the strength of a linear relationship between two variables and lies between -1 and 1. The closer you are to 1 or -1, it means the stronger the correlation, and the closer you are to 0, the weaker the correlation. The negative ones means negative correlation, and the positive ones will mean positive correlation. So these are, I don't think there's anything special there. So you can also create a matrix that gets pairwise correlations for all the numerical variables in the data. So the last variable is, we are not interested in that. It's just the indicator for whether someone is positive or negative for diabetes. So we kick it out and retain the remaining variables and apply this function. It will give us a matrix. So the output should be, what have I done? The output should be a matrix that gives us the pairwise correlations. So you can see that's the matrix. So it can't fit in one line, so it has been carried over to the next line. This batch has been sent down. But there's a slightly different way of getting correlations, and you can do that using this library. This core plot. When you plot this now, instead of a matrix of numbers, you have bubbles, which there's a color bar here. This bar indicates these redder ones are the negatives, and the blue ones are towards the positive direction. Looks like there are not many negative ones. These ones, the diagonal, are not very useful because you are checking a variable against itself, so it's not very useful. So another thing you can do is to plot pairwise scatter plots. You can also use ggplot for this later if you want. When I wrote this much earlier, I think I had not started using ggplot, so I just use the base R for plotting. So this can quickly show you the relationship between different variables. We just picked the first three variables: pregnant, glucose, and pressure. You could also do that with these pairs. If you wish, you can color them using the diabetes column and see whether there's any pattern. So the only problem with this, if you use all of them when there are too many, it's difficult to keep track. If the variables are too many, this will not be very useful, but it can give you a quick visualization of the relationship between the different variables, this matrix. So before we now try to run some linear models on this, we can look at some examples of how we visualize correlation. So this first case, I will run it, and we see the, oh, I've selected and left out something there. So I don't know how well you can see the screen. So you can see this is just simulated stuff. We've generated this data. It's not but deliberately generated. So you can see there's very little change in the y as x changes. So this means there's not much correlation between the change in y. X does not significantly affect the changes in y. So that gives it very low correlation. In this case, it's negative 0.2. So when data is in this form, usually you will have fairly low correlation. This is not the only form for low correlation, but this is one of the ways to check for low correlation. In other words, the change in x does not seem to affect the changes in y that much. So the next set, again, is designed to show positive correlation. So you can see positive correlation. What happens? The majority of the data lies in this quadrant and this quadrant. There might be some that spills across, but the majority will lie here and here for positively correlated data. And again, you can see the correlation is quite high. It's 0.93 when you run it. This last function gets you the correlation. It's quite high. So the next one again is for positive negative correlation. Again, for negative correlation, you want most of your observations to be in this quadrant and that quadrant. So the reason we are doing this, we are assuming the mean is 0 for both variables. But if the mean was different, then you'd have to use these two lines through the means of the variables. The same way we did it for the, I think I can find the previous plot. It's not going back. Oh, it's gone back really fast. So you see the reason we are using the X and Y axis there is because let me keep scrolling to get the, I'm trying to use a shortcut, but it's not working. Maybe I should just go back and run the line. But anyway, I think you saw it earlier where we plotted through the two means, and then we can check correlation using the by looking at the position of most of the data in the quadrants determined by the two means. So, but in this case, all the ones we're working here are chosen to have mean 0 on both axes. So we're using the X and Y axis as our to determine what the correlation looks like. So we have already seen this, the negative correlation. That's what it looks like. What about this last one? Now this, we have a quadratic correlation. Doesn't seem, the points don't seem to lie on any straight line. And also you can see the linear correlation is very low. Because this measures linear correlation. If you have data that doesn't lie on a line, it's unlikely that the correlation will be high. So that covers the 4 different possible cases. It's possible to generate other examples where correlations are also low, but those are 3 different. Now you can it's possible to do some transformations. I don't think we'll do transformations today. There are certain cases where you can do transformations to make the data more amenable to linear regression. So we're going to now attempt to run some models on some data. I think I have run. Just give me a minute. Yeah, we resume the PIMA Indian data later when working with multiple regression. We'll explain that. So later on, we will go through the theory. I will bring in the notes, then we run through the theory. I'd shared a book though, textbook, which you can use to be reading the theory before you can look at it. So here is an example of simple linear regression. We're going to look at these 2 variables. This is a measure of age in years up here, and the maximum heart rate down here for corresponding to each person. So this person was 18 years old, and their maximum heart rate was 202, and so on. Maybe they took many samples, and this was the maximum. So we create these 2 variables. They could be in if you wish, you can put them in a data frame and work with them in a data frame. Again, as usual, you do some exploration. When you plot the 2 variables, you can see there seems to be some negative correlation. So we will run the linear model where we regress y on x. You are familiar with this notation? For generating the linear model. Again, you have all gone quiet. Is anyone hearing me? Or?
Yes, I can hear you clearly. Okay, well, on the notation.
This is how to generate a linear model, this LM function.
Maybe the class can respond. Okay, me personally, I've encountered it in the past.
Not about encountering, but understanding. You know what it means.
Yes.
So I can assume the rest also know.
No, maybe you can also get views from the rest.
But it's not entirely new. You must have done this at some point. The other courses that cover this, maybe slightly differently, but they do cover them. Or were you using the GLM? Watu wanaogopa kuongea ama wako ndani ya restaurant? Eh? Okay, so should I assume you? Huh?
Linear models. I don't think we've covered it before in any other course, but maybe maybe a better question would be, who is not familiar with this? That's the only time they can talk, I think.
I think that question was implicit. Anyone who was not familiar, were they afraid to respond? I don't know.
I think we've interacted with it before, but if it is about the signs, like for example, y then tilde sign x, like we don't know it's a tilde, it's not anything else. I mean, personally, I don't know why it's not that, but I've used linear models before GLM, but I don't know why it's a tilde sign and it's not something else.
So this is just a formula. If you want to, so the assumption here is that y is your dependent variable and x is your independent variable. So you want to predict values of y using values of x. So you write it as a formula. So this tilde symbol here simply means you want to get regress y on x. Am I making sense?
Yeah.
So if you're working with the data frame, there's a slightly different way you'll do it. You can just put the variable. We shall see that in a minute, but this is a simplified way of just looking at regression, where you don't have to deal with any other arguments in this function. You just deal with the variables first.
So it's just like is that just a way of writing formulas in R, or like generally, or is this is just in linear models?
In general, that's how you write formulas. But for now, we are dealing with linear models, so we can focus on linear models. So this is a formula telling you that you're trying to regress y on x. So you're going to treat y as your dependent variable and x as your independent variable.
Okay, thank you.
So the order matters. You can't. The order should not be random. So I don't know if that answers your question.
Yeah, it does. Thank you.
But when you are doing this, okay, we can always get back to that later. So if you run this, this LM, it will generate the model and store. We created this variable lm.result. So this is just a variable name. There's nothing special about it. I don't like using the equal sign when working with R, so I'll change this to that. So lm.result is just a variable that will store the output of a model. So I will run this, then you will see. If I want to, draw the regression line, I simply use this command upline. Then I put my model inside the brackets. If I run this, it will draw the regression line, right? So it has plotted. We have the scatter plot for the raw data, and then now this is a regression line. Now, if you want to get a summary of the model, you apply this function summary to the model. So then this is the model. We run this and we'll see what the summary looks like. Okay, so so this gives you some statistics on the residuals, the minimum. You know what the residuals are? In any case, we shall cover this in the theory part. I'm trying to just show how you generate these models and also making some assumptions that you have a rough idea of what a linear model looks like, but we shall do the theory separately. So at this point, there's some assumption I have to make that you have a rough idea of what it is, but later on we shall look at it and you'll understand what I mean. So you can get the coefficients if you just want the coefficients only, because maybe I need to do a quick. Okay, I'll just run this. So there's the intercept and the coefficient of the x variable, which is produced by this command, coef lm results. You can also do the same using this. This gives you the same output. If you just want the intercept only, you can pick the first component in this result for coefficients. If you want, if you want the second one, you can change this to 2. So or you can also just use the. Let me run this so that you see. You already know the coefficient here is 210, and the intercept is 210, or the constant term, and then the, what do you call it? The coefficient of x is minus 0.79. So you can double check that these pulls out the same values. So that gives you the intercept. This one gives you the coefficient of x, the same values again. So if you just want to extract those separately, that's how you do it. And maybe from the summary, you can also tell. You can see this one is called x, then the intercept is here. Now, you can check the significance of each coefficient. So you can see in this case, if you're working, say, with a, it doesn't matter which one you pick. This is highly significant for both cases. It means it says the model is quite strong. So the other thing you normally look at is the R squared. This one is quite high. It says 90% of the variation is explained by X. 90% of the variation in Y is explained by X. So it's a fairly strong linear model. Is that making sense?
Yes.
So
yes, it is. Mwalimu, do we have a like an acceptable range of R squared?
R squared is supposed to be between 0 and 1. So the closer it is to 1, 1 is perfect, and 0 means bad. Now, there's no, I wouldn't say there's a perfect R squared that you should pick. A lot of it depends on the domain that you're working in. So there are certain practices. If you want to find out whether it's ideal, you may need to check the literature in the domain where you're working. So there are variations, depends on what you're working on. But the higher it is, the better, definitely.
What about the adjusted R squared?
So in this case, the adjusted R square is not so important, because the adjusted R squares sort of takes care of the problem with the other R squared.
Okay, thank you.
It
So
is Is someone asking a question? So the R squared on its own usually is keeps increasing. If you increase the number of variables, it keeps going up. So the adjusted R squared sort of adjusts for that. So that the R squared is not inflated just by adding more variables. But in this case, you have only one variable. So the adjusted R squared may not be very useful for us. It makes more sense when you have more variables, in which case the R squared itself may be exaggerated when you have several variables.
Okay.
Yeah. But we will, at some point, we will go through the theory. But feel free to ask the questions. So this is just stuff on the coefficient. So you can also predict. So for instance, if you have to do the predictions, you require your data to be in the form of a data frame. So suppose someone is 50 years, based on this model, if someone is 50 years old or 60 years old, what would be their maximum, what was that? Was it maximum heart rate? Of course, when you are drawing this, you have to label your axis appropriately. Since we are just in class and focusing on the theory, I've not focused on the aesthetics for these graphs. So if you want to do a prediction, you will use this function predict, place the model here, create the data frame that contains the let's start here before we add the other arguments. We'll create a data set that contains the two values on which we want to predict and then run this. So it will give you the, was it heart rate? Let's run this. So we expect someone who's 50 years old to have an average heart rate of 170. Someone who's 60 years old, we expect them to have an average heart rate of 162. So those are predictions. So these are maybe values that are not in the, you see we don't have 50 and 60 precisely in here, but we can predict. So one thing about linear regression is it may not make sense to predict for values that are outside the range. So you simply create a small data frame containing values of X and use it as your data for the prediction, and it will give you the corresponding heart rates. So let's do the next one. So this next one, we have done the same thing, but we have added some more arguments. So we want to work at a 90% level of confidence for our confidence intervals. And we indicated that we want the confidence interval. So if I run this, it will give me the different fitted values, and then it gives me the confidence interval. So the fitted value for the first value in your data was what? 195.68, and then the lower limit is 192, the upper limit is 198. So we expect the first one was, I can check, the first one had a weight of what? I think this is sorted. Yeah, but these are the confidence intervals, basically. These are just confidence interval of these predictions for the data. I think you have only 15 people, and these are the predictions, right? Is that making sense? So these are just the confidence intervals. If you use ggplot, normally it can plot these. It normally plots a band around the regression line. Then you can see them graphically. So this one is simply out of this matrix. This is extracting the lower confidence interval, the upper confidence interval, and then it will plot them in the graph. So this is sort of a poor man's way of plotting these on the graph. I will add them now using these commands. So you can see now you add the confidence bands. But if you're using ggplot, normally does this automatically and then shades. It can add the standard errors. But now here we have just extracted them and plotted them on the same axis. So the main regression line is this straight line. Then the errors, I think it has more errors as you predict lower values and higher values. There's a higher chance you'll make an error. There's less error as you predict the values in between somewhere halfway in between. You can see the error is smaller. So this sort of takes care of simple linear regression. I've not dwelled on the results, but you know how to predict. You understand what these p-values mean. Eh? You are checking whether the intercept is significant or the coefficient of the independent variable is significant. So these p-values will tell you based on your significance level whether these two are really small. So it definitely means it doesn't matter which, whether you pick 5% or 1% significance level, they will be significant. So this tells us that this is good for, reasonably good for our predictions. But again, we shall do the theory later. Right now, I'm just focusing on how it is applied. Are there any questions on this? Kuna maswali? So the next one we'll look at is a situation where you have more than one variable. So we'll start with a sort of rigged equation. So you have a dependent variable and then you have two or more independent variables. So you want to predict values of Z in this case when you know values of X and Y. So we'll generate some values of X and only 10 of them, and also another 10 values of Y. Then we'll create another variable Z, which is simply given by X plus Y. So here we are basically rigging. I don't know whether I should I'll stop sharing for a minute and see if I can get the whiteboard. So I have not used this blackboard before. Let's see, where is the pen? Oh, they're down here. So yeah. So essentially, the first case we were looking at is where you have only one independent variable, and you want to predict, you have one dependent variable, sorry. Well, I'm mixing. We have one independent variable. The dependent one is always just one, whether you're dealing with. So usually the idea is that you expect this to be the actual regression line, but there's usually some error involved. We shall illustrate that. So the current case we are looking at is where you have one dependent variable, then you have a constant term. So you can say B1. I think a better way to do this is get the eraser. I need to get rid of this. Let's get the pen again. So we have y is supposed to be, we'll use now the usual mathematical notation, alpha not as your constant term, alpha 1, then you have one variable. This can go on as far as you wish, as many variables as there are in your model. X2. Because sometimes one variable may not be sufficient to explain all the variation in the dependent variable, and you may need to add more variables to increase the strength of your model. This can go to as many, but I'll just stop at 2 for now. When you're dealing with the theory, we'll deal with the general case. So this is the kind of thing you expect. So in real life, there will always be some error in your measurements, but this is what you expect to be your perfect model. So this is what we are going to generate. So we are going to fix values of x1 and x2 and generate values of y. In the
Sorry,
file, what? Pardon?
Are you sharing a screen?
Yes, I told it to share the whiteboard. I'm writing. I don't know if you can see what I'm writing.
I don't know if it's just me, but I cannot see it.
I
Can't
can
see anything.
I can see.
Yeah, I think it's my connection then. Sorry, go on.
Is there anyone else who cannot see? So the one we have now, we have used z as our dependent variable, and then we have x and y as our z is a dependent, x and y as our independent variables. And then so we have assumed the coefficient of x is 1 as we generate value of z, and also assume the coefficient of x is 1. So we'll generate data based on this and try to find out if the linear model can actually recover these coefficients correctly. I don't know if that makes sense. So we are going to pretend we'll generate it knowing the coefficients are 1 and 1, and then run it through the model and see if the model will actually recover these coefficients. But in the model, instead of, I think we will add some error. We'll add some error terms in the model and see whether the error significantly affects these coefficients, right? So all this will be done again in theory. For now, let me share the R code again. Was I sharing already? Can you see my R file, the R studio on the screen? No.
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 Okay, now you should be able to see it. You can see
Yes.
the R Studio.
Yes.
So what we're going to do, we'll generate some values for X. We also generate another 10 values for Y. We'll sample 10 values from the numbers starting from 1 to 100. We sample only 10 values. But here we just give increasing numbers from 1 to 10, increasing by 1. Some of these I think you're familiar with, how to generate a sequence of numbers with increment of 1 and how to sample a vector. So we are just going to take a random sample of 10 numbers from this vector. So X and Y now each have 10 values. Now we'll create a new variable Z, which is X plus Y. And also we assume the constant term is 0 in this case. So we'll create Z. Now you have X, Y, and Z. Then how you run the model again is simple. You have LM, then you have Z. You regress that on the two variables X and Y. So if you have multiple variables, you use plus to keep in adding the variables. This plus sign, if you had a third variable, you'd like maybe there was a T as a third variables, you'd have to put X plus Y plus T, but now we have only 2. So we are going to check what will this model do for us. Will it recover these same coefficients? So I will run this. So you can see it has given us a very small intercept. In our model here, the intercept was 0, right? The way we set it up, because Z is just X plus Y, there was no intercept, it was 0. And the linear has also just found 0. Usually R represents 0 as a very small number. So this is 1.685 times 10 raised to negative 14, which is a very small number. It's just 0. And you can see the coefficient of X is 1 and the coefficient of Y is 1, exactly as it was in the model, right? But in real life, you rarely have perfect relationships like this, where Z is equal to X plus Y. So now what we'll do is we'll add some noise to the model. So we're going to generate new values of Z, but values that have some noise. So they look a little more like real life data. You're familiar with these functions for generating random normal. So you want to generate 10 values that are normally distributed with mean 0 and this standard deviation 10. So I think some of his comments were, oh, no. There's this one here. There are two cases. I think I'm looking at the next one. The first one, the sigma was 2. The next one, the noise was 10. So if it has a lot of noise, if it just has a little noise, if the standard deviation is 2 for this normal distribution, it's not a lot of noise. So we don't expect the coefficients to change that much after adding this small amount of noise. And when we do that and run the model, you can see the output. It gives us the intercept 0.8767 and which is also not 0 but not far from 0. But now because of the noise, it now has an intercept. You can see the coefficients are also different from 1 but not very different from 1. Okay, so you're still able to recover the coefficients even after adding noise to the data. So we could go a step further and add a lot of noise to the data. So if we increase the value of a standard deviation here for this normal distribution, it means you are adding a lot more noise to the data. And then when we run the model now, you can see it is not able to recover the coefficients properly. It actually gives us an intercept of 14, yet the original model that we generated, it was supposed to be 0. So the noise has really disrupted the generation of the model. This again is not as close to 1. The only one that seems to be recovered fairly well is the coefficient for y. So, but if you are running a case where you want to make sure that the intercept must be 0, you can add this -1. So if you run this with -1 there, it will ignore the intercept and you only get the coefficients of y and x. But again, remember, we have added a lot of noise to z. So you can see the x coefficient is not as close to 1, the original coefficient 1 that is there in the simulated data. So we can get the residuals.
You got this big machine, brother. I just can't. It is impossible. Any machine kubwa, lakini haipitiki.
Hey, we have some entertainment. There's someone whose microphone is on. Mezima. So if you want the coefficients, you can run the summary, store it in this, then you can get the residual is just the difference between the predicted and the observed values. There are multiple ways to get it. You can get it like this, or we get them out like that. If you use tidyverse, there are some functions in tidyverse which make it much easier for you to do this. I think when we do the theory, we shall run a more compact analysis. When we do the theory, we will still do some R work, but we will run a more compact analysis. So now we can go back to our PIMA Indian data set and try to regress triceps on mass, right? And save it in this variable called model. So when you do that, this is what you get as we already drawn the graphs for this. So I will not draw the graphs again. So we can get a summary of the model. It's just a single variable case. Here it gives the intercept as -3. The coefficient for mass is roughly 1. And it says both of them are significant if you work with a 5% level of significance. This one is definitely significant at 5%. This one doesn't matter which level you pick. The p-value is really small to be significant. So if you look at the R squared, it's 0.42. So it means this body mass index does not completely capture the variation in triceps. It does capture some variation, yes, but it does not fully capture. It only captures 40% of the variation in triceps. So if you want to describe triceps, mass will not give you the full information. You may have to add a few more variables to check if mass can actually predict triceps accurately. So this table, I think, is fairly straightforward. These are the coefficients. You have the standard errors of the coefficients if you're interested in looking at that, and then you have the p-values to tell you whether the intercept is significant or if the coefficient of mass is significant. In this case, they are both at the 5% level. So I think this is what I was talking about earlier. If you can run the same variables from that data set and draw the graph. So here is a graph. This ggplot draws those confidence bands using this option for standard error. SE is equal to true. If you make it false, then you'll not see these bands. So this straight line fit, this is a straight line fit for triceps against mass. It's not a very good fit in terms of the R squared, but it's reasonable. You can still use it to predict, just that it won't account for all the variation in triceps. And you can see around here, there's a lot of variation. So there might be some other variables that account for that variation that is not picked up by the body mass index. So you can also make predictions. So we can suppose someone has a mass of 30. What is this measurement for triceps? I think it was something about thickness of the skin. We run this and see what happens. So if you're predicting, and we've already told it to also include the confidence interval. So it gives us a prediction. The triceps measurement would be around 26 for someone with a mass of 30. And it can be as low as 25 or as high as 27. So that's the default confidence interval. I don't think if you, this one still does the pair plots. This library psych has this function that does the pair plots. Although ggplots also has some function for pair plots. Maybe later on we'll look at them. What has happened? It's supposed to, yeah, it was taking a bit of time. So the advantage with these pair plots that come are done by this psych package is it includes the histograms for each of the variables, and then it also maps in it does the straight line fits. So this linear model is fitted. If you say LM is equal to 2, that option fits you can remove this. If you make it false, then it won't draw those straight lines. So if you run this as false, it will not draw those straight lines. It's not running. So this is just another way of doing the pair plots. So now we are trying to regress triceps on mass only. We can try to check if we add these two other variables, instead of just regressing it on one variable. What happens if you regress it on two more variables? Will the model improve? So I will run this. Previously, we saw that the R squared value was 42%. Let's see what happens now when we add two more models, two more variables. So it doesn't seem to have improved much. The multiple R squared is still 0.42. So it means maybe these variables don't add as much value. For instance, it shows pressure is not significant. This coefficient for pressure is not significant, doesn't seem to contribute much to the triceps measurements. Glucose and mass seem to be significant, but this one is not. The intercept is also significant at 5% level. So we haven't improved the R squared by much. It means this adding these two variables, these variables is not very helpful. And we've also observed that pressure is not very useful. You could also just try all, if you want to use all the other predictors. So you put mass, then you use this tilde and put a dot. In this case, we have specified the data since we are picking the variables from this data file. Unlike previously when we were just generating them directly, we didn't have to specify the data argument. Now, if you run this, with all the variables, the multiple regression R squared is slightly improved to 50%. You could also do the summary and see which of the variables are significant. So there are many variables, not all of them are significant. Like pedigree and age don't seem to be significant. Diabetes is significant at the, what do you call it? At the 5% level of significance. And here it basically codes this diabetes and use one of the possible values for diabetes as a reference. So you can see all the variables here. Only this glucose doesn't seem to be significant when you run it with all the other models. All the other variables rather. Pedigree doesn't seem to be significant. Age doesn't seem to be significant. And so on. But these two seem to be highly significant. Pressure, triceps. And what else? The intercept also seems to be significant. Highly significant. These stars tell you that. So we shall do all this later. Right now, we are just trying to get the hang of it. We'll run through the theory. So you can run it without the variables which are not significant. So if you want to exclude variables, you can use this tilde, put the full stop here. Then the variables that you don't want included, you remove them using minus glucose, minus pedigree, and minus age. So these variables will not be part of the regression. All the other variables will be included except these three. So this is a shortcut for doing that. And when you do that, you see again, now R squared is around 49%, slightly improved from the 0.42, and then you have only kept the variables that were significant from the previous analysis. So this next one does something similar to what we have done before, but now uses three variables. So you sort of rig using three variables. You can change these coefficients if you want to have something different from things that don't just have coefficient one. actually, yeah, this is fine. The coefficients have been changed actually. In this case, we have done some what do you call it, generation. I'll come back to that. I thought that was not necessary to cover, but I've seen there's some additional concept there that will be useful. So this one is just I think this is some World Bank data I had gotten. Downloaded from one of those websites. World Health Organization, not World Bank. It had several variables, but I picked only 3: weight, height, and the upper arm length. Then did the pairwise plots. So here you can see that the relationships between these variables are not linear. They don't look linear. You can see they seem to follow some curve. Maybe with the exception of these two, height and upper arm length, seem to have a linear kind of relationship. The others, like height and weight, don't seem to be exactly linear. They seem to follow some curve that goes like that and so on. Also, if you look at weight and upper arm length, they seem to follow some curve. So this may be a good candidate for transformation. So this is another data set. These are the variables in the data set. It's just this weight, height, and then upper arm length measured. When I'll send you this file, you can look at the file in detail. So we'll get a subset of the data set containing just these 3 variables. These 3 variables of height, weight, and upper arm length. That's what is happening here in this last line, in this line. So this new variable BM2 simply contains those 3 variables out of. If you want to see what I'm working with, we can view this file so that oh, something has gone wrong. So we can look at what is in this file. Let's view it as a spreadsheet. So I don't have the file that has the metadata on this, but this is a file. It had over almost 10,000 entries and 33 columns for 33 variables. So a lot of missing values, but I picked just 3 of the variables. So these are codes. The variables were coded. So you'd have to go to the file with the metadata that tells you more about the variables. But essentially I picked the variable, these 3 variables: BMX, that's the weight; BMX HT, that's the height; and BMX ARML, that's the arm length. So these are the only 3 variables we pick from that file, and we work with those. And when we draw the pairwise catapults, this is what they look like. So since there are a lot of missing values, we just, for now, this may not always be the case, but we just pick the cases that are complete only. So the next line here only extracts the cases that are complete with no missing values. And we run that. So now I think we've already done that. That's what this plot does. So we can extract the height, which is the third variable in our data frame, and also we can extract the upper arm length. I think it's a second variable in our. Oh, the height is x1, so height must be the second variable. Height is the second variable. You can even see here. And then the third variable is the upper arm length here. So we store the upper arm length in this variable y1 and the height in this variable x1, and then just plot those two first. So these ones seem to have a linear relation, fairly reasonable linear relation, positive. So you may be able to predict fairly accurately the upper arm length. Sorry, x was what? X was the height. You may be able to, based on height alone, you may be able to fairly predict the upper arm length for this data. So now, when the data set is really large like this, it can be a problem to visualize. So you can take a smaller sample. We just take a small sample of 10 out of this data to illustrate the concept of regression. So we'll run this. We picked out of all the rows in the data set, we have picked 10 at random. And then we use those 10 to subset both the x and y. X was height and y was what? Arm length. So we use these rows that we have picked here at random to subset the data, so that we have only 10 data points for our purposes. So you can see what they look like. When you have 10 data points, it's not so good, but it still seems to pick the linear relationship in general. There seems to be some gaps here in the middle. While it was sampling, it ignored those. So you could also try, when you have very large values, you can transform them using the logarithm. So we can transform both axes to logarithm. With ggplot, you can do this straight from there. Now you can see the plot after the transformation. Both the x and y axis have been around the log scale. So this might be a better linear model. It looks better. If you want to test it with a larger number of samples, you could change this, say, to 100. Let's work with 100 so that I'll replot it again. Now, when you have 100, you can see the sample is larger. This is before the transformation. When you transform, this is now what it looks like after transformation. Seems to have a better linear relationship. Let's model the two. We get the summary of the model. You can see the R squared is quite high, 95%. And both the intercept and the coefficient of log x, the transformed variable, are significant. So this is just getting the coefficients. You've already seen them here. There's no need to. If you want to get the fitted values, you can extract them using this attribute, the fitted values. You can predict. Now this is the transformed data. You can predict values of y using transformed values of x, and as well include the confidence intervals for each predicted value. So for this value of x, 4.2, the prediction is about 2.6 with the lower confidence interval, lower limit of the confidence interval at 2.5 and the upper limit at 2.6 and so on. The same is true for the other three predictions. So this is just prediction for these three values of the transformed data. So you could do the plot and add the regression line of the transformed data. This time we have put some labels and colored the regression line red. So this upline is what fixes the regression line here. I will just run this so that we see what I will select all these and run. So it seems to have worked. So if you look carefully, what it has done is it has plotted some, what you would call the, it has joined, this value is the actual value, the predicted one is the one on the line. So it has joined the actual value to the predicted value on the line for each of these points. So these are the errors in measurement. And usually you use the least squares optimization. In this case, you get the minimum. This regression line is supposed to give you that minimum least squares. So you get these residuals, square them and add them. The line that gives you the smallest value for that sum is your best line of fit. But now this illustrates the residuals. So you get the actual observed value, the fitted value lies on the line, and so on. So this next one simply plots the fitted values. You pick the fitted values and plot them with the corresponding transformed values. So this should appear on the straight line. You can see the fitted values will appear on the straight line. So this is easier to see when you're working with a smaller sample. So that's why earlier we had put 10. But now these what you're seeing as gray values here are the fitted values. They would, but now they correspond to each sample. So for instance, this is observed value, and this is the fitted value. If you want to put both in the graph, that's how you do it. I think. Then you can add the values as well. Using this text command. So the text, when there are too many, it's hard to see. Let's run this with just 10, a sample of 10, then it will be clearer. All this that we're doing will be clearer. But ideally, you will not be running a model. Most of the time, your model should have more than this. So you can see when there are fewer, you can check the predicted and observed. Then I will continue running. Now we have the predicted values, these gray ones, but they will just lie strictly on the straight line. So like here, the predicted value and the observed are quite close. For this one here, the predicted and observed are slightly apart. For this one, I think it has the highest error among the ones measurement. The predicted one is on the line here. The observed one is down here. This one has the highest error, so on. Then you can use this to label. This labels the points and puts the actual values. Again, there are still too many. So but what it has done is the following. So you see here the observed value is 3.5. The predicted value is about 3.483. That's what these labels, these two lines are labeling the points, the values for the predicted and the values for the observed value. So if you wanted them labeled, like most of the time you won't be doing this, but this is for learning purposes. So let's do this last one. I think this last batch will. This will bring us to the end. So now here we'll consider multiple regression. But then we have three variables which will generate. You have U, V, and W. Those are going to be our independent variables. We have generated, we simulate them like this. Then we also simulate the error term. We have a mean of 0, the standard deviation of 5. Then we generate an dependent variable. This time we include a constant term as 5, 4 as a coefficient of U, 3 as a coefficient of V, and 2 as a coefficient of W, plus the error term. So this is going to be our model now with the error term. So let's run all this. So now we have we can now try to fit the regression. Observe the following: the constant term is 5, the coefficient of U is 4, and that of V is 3, and that of W is 2. So we want to see if this linear model will recover these coefficients given the data. So usually you don't have these values, but you have the data. So now from the data, can we be able to recover these coefficients? So you just run the model and you can see the intercept is 4.617, not very far from the actual intercept. The coefficient of U is 4.2, again, not very far from the actual value. So, but the reason it won't be exact is because we have an error term, right? If we didn't have the error term, it would recover the exact coefficients. But the ones recovered are not so far from the actual values. So that's why you normally have some confidence interval to confirm that the true values should lie within that confidence interval. But these serve as good estimates. So now we are going to put all these in a data frame. If you have them in a data frame, then how you specify the model is this is what the data frame will look like. We have all these variables Y, U, V, and W in the data frame. So we do the regression here of Y on U, V, and W. And since now we are using a data frame and we are picking the variables from the data frame, you have to specify the data. So the data is being obtained from this data frame, which we call DF up here. So this is the same regression we have run earlier, but now we're just doing this on the data frame. If you just wanted to use all the variables that you didn't want to type out all the independent variables, you put the tilde sign and put a dot. It will run on all the remaining variables. Is that making sense? So if you want this, let's save the model in this variable called M and try to get the summary statistics. So the summary statistics, we have R squared is about 73%. The adjusted one just goes down slightly, still 73%. So this, what is commented out is just the output that was obtained. If you want coefficients, you can use this line that gives the coefficients. This gives the confidence intervals for the coefficients. This gives you the model residuals. We shall do this in some detail later. We normally expect the residuals to be normally distributed. So if you check the histogram for the residuals, it should be symmetric. This is roughly symmetric, so it makes sense. You can compute the residual sum of squares without formula. You can run the ANOVA table. So later on, I think when we're doing the theory, we shall look at these ANOVA-like tables and explain them. So this one clearly says the three variables, U and V and W, the coefficients are significant. Again, we have to state some hypotheses. In the theory, we shall see how we state the hypothesis for these coefficients. So I think I'll stop there. The next one talks about variable selection, but it's something that you barely get to use. So maybe what I will do is this one. This library called Broom, if you load it, and then you apply, in that library called Broom, you have this function called augment. If you apply it to the model M, I think it augments the data to the output of the model. You can view what is an augmented. So this is what you see. What happens? This was the data. So if you augment the model, it will bring the data along with the statistics. So there's the fitted values, the residuals. For now, I think those two are the ones we are interested in. These are additional statistics that help you check how good the model is. We will not look at them now. There's the standardized residuals also. But these two, fitted values and residuals, are the ones of interest now. So now that they're already part of this data frame, they've been augmented, you can just draw the fitted versus the residuals, do a scatter plot of that, and you can use that to tell whether your model is good. So if your model is good, they should be sort of randomly distributed along this line, y is equal to 0. So the same plots can be obtained by just plotting the model. You pick the model and feed it to this function plot and tell it to plot. Ideally, if you don't specify this, which is equal to 1, it will give you 4 plots, but you are now interested in only this one. So this one sort of gives you an idea of the fitted versus residuals. So it draws a line y is equal to 0, the dotted line, and then tries to fit a straight line for this. So the red line is usually supposed to be not too far from the line y is equal to 0. So this graph is the same as the previous one. We plotted it manually here, but here we have just pulled it out of the model by using this command plot. So if you don't specify which graph you want, just tell it to plot M. It will plot should give you all the 4, I think. There's usually 4 diagnostic curves that will come up. If you run this, it will give you 4 of them. If you press enter, you should get the next plot. So this is the second plot. The third plot is this one that does the standardized residuals versus the fitted values and so on. Then the final one is this leverage. Again, this is we'll leave this for now. This I don't want to go into the details. It's useful for checking influential measurements and so on. There's this library called CA. It also can help you check for outliers. So one of the outliers is the 81st value. And then you can check, if you want to check if indeed it's an outlier, you can run this influence.measures on the model. And 81, which was picked out by outlier test, you will see it is also starred here when you run the influential measurements. This will make sense once we go through the theory. So for now, I'm just running through the code so that you get a feel of the code. Then when we go through the theory, this will make a lot more sense. All these figures. So the only thing I've skipped here is a variable selection. It's unlikely that you would use that much anyway, but I've skipped it. But the main idea behind this course is to do the optimization. So in the theory is where we shall look at the role of optimization in this. Some of you may have done this in class already, but now we're going to, maybe some of you who already did statistics at some point, you may have done this in class already, but we shall now look at it closely. So are there any questions? So I will share this. There's a folder which I will share that contains this script and the corresponding data files that go with it. So you can play around with it yourselves. So I've tried to put as many comments in here as possible. Hopefully they will make sense. Although now when I talked to the class last time, you said you are at intermediate level for both Python and R. Though for some of the things I'm asking, there's hesitation in admitting whether you know or not. So I don't know what level you are. That makes a big difference in the approach. Or what level most of you are. So the assumption is that in the first semester you had a lot of encounter with the coding, and so coding now should not be the focus of the course. But if there's anything you don't understand, you're always free to ask. You don't talk much, man. Unaonekana mmechoka.
Daktari, we are there actually. Yeah, that account is true.
What is true?
Okay, yeah, what we have just said about the coding and yeah, we were introduced to coding in the first semester.
Okay. So
Yes.
should I just assume that you'll be able to follow the code? I do not need to bother too much to.
I think we'll try to follow, and then if we encounter any challenge, then we can reach you.
Okay. So
Yes.
the one that we will do with the theory will be a little more interesting.
Okay. Okay, and Dr. maybe if I can add,
Yes.
I think there are some guys who have a problem in using this platform, that is the Teams.
Yes.
And they are requesting if you can use Google Meet next time.
The advantage of this is I'm able to record.
Yeah, because they are trying to say that they have accounts in their respective organizations, and now they are forced to switch kind of when they are joining this class. Yeah, that's what I'm hearing from them.
I don't understand what they mean by accounts in.
Yeah, maybe I think Moses probably can explain.